Okay, so our last video for this week is an introduction to basic set theory and set notation. So first I'll just start by defining what a set is. So a set is just a collection of distinct objects. And we have specific notation that we use. In particular, we use curly brackets to denote the limits of a set. So any object written inside the curly brackets, separated by commas, denotes elements of the set. Part of the definition of set is that the objects inside are distinct. And as I mentioned, we write curly braces to denote what objects are contained in the set. Some nice simple examples. Let's say S is the set that contains the numbers 1, 2, 3, and 4. We would write S equals braces 1, 2, 3, 4. This set has 4 distinct objects, 1, 2, 3, and 4. We could say, let's say the set A contains the objects 2, 1, 3, 1, 4. It doesn't matter what order we put the objects in the set, because it's just a collection of objects. So this, we'll notice that every single object in the set is also in the set S, and vice versa. Every object in S is also in A. We have a repeat here. We have 1 written twice. It doesn't matter how many times 1 is written. We're only interested in the distinct objects inside A. So this is the same set as the set 2, 1, 3, 4, which is the same as the set S. They contain the exact same objects. Another example of a set T will be the set, so this is other notation. We write the set of X line means the set of X such that X is an even integer. This set is the same as the set that contains 0, 2, 4, 6, etc., -2, -4, etc. This is just a special notation for writing that. A couple more special examples. A very, very special example is called the empty set. We denote that with a 0 with a vertical line, or sorry, a sort of slanted line through it. Another way of denoting it is with braces with nothing inside. This is the set that contains no objects. Another term you might hear is null set. It's the same thing. It contains no elements. However, the set, the empty set itself is an element, or it is an object. It can be used as an element in another set. But it itself contains no elements. Okay. Some other examples of number systems that you've seen in other courses. Bold-faced n is the set of natural numbers. These are the counting numbers, and depending whether you're in the United States or France, it either starts at 1 or 0. For now, let's start it at 1. Boldface Z is the set of integers. Q, boldface Q is the set of rational numbers. So these are fractions of integers. R is the set of real numbers, and C is the set of complex numbers. Notation, when an object is the element of a set, we use the following notation to indicate it. So we say X is an element of S, or X is in S. Additional notation, we can talk about the number of objects that are contained in a set, and we call that the cardinality of the set. So if S is a finite set, we will write we'll use the absolute value symbol or vertical lines to denote the number. And remember, this is distinct, the number of distinct elements in S. Okay, so the number of elements in the set S we call the cardinality of S. So as an example, let's let, as before, S is our set 1, 2, 3, 4. S prime is our set 1, oh wait, I think it was 3, 1, 2, 1, 4. And we have the empty set. So that's 3 examples of sets we've seen. So pause now and see if you can find the cardinality of each of these sets. All right, so we've already discussed that S contains 4 distinct elements, 1, 2, 3, and 4. So that means that the cardinality of S is 4. We also already saw that S prime was actually the same set as S, although we called it A last time, because it has the same elements. 1 is repeated, but it has the elements 1, 2, 3, and 4, and only those elements. So the cardinality of S prime is also 4. And what do you think about the cardinality of the empty set? So the empty set contains no elements whatsoever. So we say that the cardinality of the empty set is 0. Okay. So I've already implied this several times, but to be very, very clear, we define 2 sets to be equal if they contain the same elements. And we'll use the equal symbol to denote equality between sets. So in particular, A equals B means that if X is an element of A, then X is an element of B. And if X is an element of B, then X is an element of A. So we can write that as in terms of a proposition, right? So this is a conjunction of two implications. So as an example, the set 1, 3, 5 is equal to the set 1, 5, 3 is equal to the set 3, 3, 5, 1. To see, for example, that the set containing 3, 3, 5, and 1 is equal to the set containing 1, 3, and 5, we can simply take any element over here, show that it's over here, and vice versa. Any element we choose over here is also over here. Okay. So our next definition is called subset. We say a set X is a subset of set Y if every element that's contained in X is also contained in Y. So anytime we have an element in X, it's also in Y. And we write the following notation to denote that X is a subset of Y. We can further call a subset a proper subset. So the term subset allows for equality of the sets, right? This is 1/2 of the definition of two sets being equal. So if two sets are equal, then certainly they're each a subset of the other by this definition. If we want to if we want to define something that says they're subsets and they can't be equal, we use the term proper subset. So as an example, the set containing 1 and 3 is a subset of the set containing 1, 2, 3, and 4. And it's in fact a proper subset because 1 and 3 are both over here, but this set over here contains both 2 and 4, which are not over here. I like to use the notation subset with a little line through the bottom to indicate not equality of proper subsets. Another notation is just the inclusion, subset inclusion without the line underneath. You might see that as well. Okay. I've already indicated this, but just to review one more time, to prove the two sets are equal, and we will get to like detailed proofs in the next topic. But in general, to show that two sets A and B are equal, we need to show that A is a subset of B and B is a subset of A. Okay. So we have two more definitions in this section. The first is called power set of a set. So like we did with propositional logic, we have certain objects that we're studying. In that case, we were studying propositions. And so the next step in mathematics, when you have a class of objects that you want to study, is to come up with ways to combine those objects into new objects. So with propositional logic, we had lots of different ways to combine propositions to make new propositions, like implications, ands, ors, negations, etc. Our objects now are sets, and so we want to find new ways to combine sets to create other sets. We'll do a lot more of those next week, but to start, now we'll have two ways. The first is called the power set of a set X. The power set of X is the set of all subsets of X. And we should be very careful here. Both the empty set and the set X itself are both technically subsets. So the notation we use for power set is curly P of X. This is the set of all subsets of X. So a quick example. Let's let A be the set containing lowercase a, lowercase b, lowercase c, and let's compute what the power set of this set A is. One way, when we have a finite set and we're trying to enumerate all of the subsets, is to consider the different cardinalities of possible subsets. There's only one subset of cardinality 0, and that's the empty set, so we can list it first. There are three, however, subsets of size 1, right? Just the set containing just lowercase a, just lowercase b, or just lowercase c. The set containing a, the set containing b, the set containing c. These are all subsets of A of cardinality 1. How many subsets of A are there of cardinality 2? Think about this for 1 second. Okay, so now the subsets of A of cardinality 2, well, that's the subset containing both A and B, the subset containing both A and C, and the subset containing both B and C. Since the order doesn't matter inside the sets, there's only 3 subsets of A of cardinality 2. How many subsets are there of cardinality 3? Only A itself contains all the elements. So that means that the cardinality of the power set of A is 8. If you do more examples, you'll see in general that if A is a finite set, the cardinality of the power set will be 2 raised to the cardinality of A. Okay, so the last thing I want to describe in this unit, or this section, is one more way to combine sets to make a new set. And this is called the Cartesian product. I'll define it for 2 sets first, but we can actually define it for as many sets as we want. So I should note that the Cartesian products are also sometimes called direct products. But you can probably safely ignore that for now. Okay. So let A and B be sets. We define the Cartesian product of these sets. We denote it with a time symbol, A cross B. That's how we read it. The elements of the Cartesian product of A and B will be ordered pairs, so these are tuples with round brackets. The first will contain an element from A, and the second element, the second entry in the ordered pair will be an element from B. So one thing that might be a little bit tricky to remember is that in a set, the elements have no order. They're just a collection of objects. But the elements of the set A cross B are themselves ordered pairs, or ordered tuples in a more general setting. So here the order very much matters. The first entry has to come from the first set, and the second entry has to come from the second set. So, an example. First, let A be the set containing the 3 pictures, smiley face, heart, and moon. And let B be the set containing the pictures sun and star. We can construct the Cartesian product, A cross B, by taking all tuples, the first element coming from A and the second element coming from B. So if we do this in an orderly fashion, we could start off with smiley face sun. We could also do smiley face star. We could also do heart sun or heart star. Or we could do moon sun or moon star. And the important thing is that the first entry is always from the first set, and the second entry is always from the second set. Another example. A could be the set containing lowercase a, b, and say X could be the set containing 1 and 2. Let's make this capital X so we don't get confused with the little cross symbol. Okay. So see if you can compute X cross A. All right, let's see if we get the same answer. So X cross A consists of tuples where the first entry comes from X and the second entry comes from A. So we could have 1A, 1B, 2A, or 2B. And that's all. Now it doesn't matter which order we write these elements. but it matters what order we write the elements inside the tuples. Okay, so we could instead write this as 2a, 2b, 1a, 1b if we want. Okay, for our very last example, we'll do one with 3 sets. So if we let Z be the set containing alpha, beta, for example, and we wanted to construct x cross A cross Z, now our tuples are 3 tuples instead of ordered pairs. And we see that the total entries are 1a alpha, 1a beta, 1b alpha, 1b beta, 2a alpha, 2a beta, 2b alpha, and 2b beta. All right. And so that concludes our third topic.